So before we start, I just wanted to say Charlie Bowman says hi.
Oh, good.
Oh, of course.
Good.
Yes.
We haven't been traveling the last few years, so I haven't gotten to see him,
Yeah,
but usually I probably see him every year or two. So it's
right.
good. It's good. Good to hear from secondhand at least. Okay.
So, Johnny, do you want to get started?
Yes.
Yeah, I think we have enough people,
Okay.
so we can get started if you're okay with that.
Okay. So let me introduce Dr. Suhas Sreehari. Suhas Sreehari is a staff research scientist in the National Security Sciences Directorate of Oak Ridge National Laboratory. He holds a PhD in electrical engineering from Purdue University. His research spans Bayesian estimation for computational imaging, signal processing, machine learning, and explainable AI. Most notably, he is a recipient of 2020 SIAM Imaging Sciences Best Paper Prize and the 2019 IEEE Signal Processing Society Young Author Best Paper Award. So today's topic is about computational imaging, explainable machine learning. So has welcome to our seminar. So you can get started.
Yeah, thank you very much for the introduction and for having me and for attending my talk. So I want to keep it fairly simple, so just a few short stories. And just before we begin, I want to have expectations be more realistic about the explainable machine learning part, where so for imaging, explainability has been, people do think about it, people work on it, but it hasn't been worked on long enough as, for example, in finance or in healthcare, where you have more tabular data than image data. So just taking some baby steps. This is fairly recent, so I just want to set those expectations. And feel free to stop me anytime. We don't have to wait until the end of the talk. So if something doesn't seem right to you, or if you need clarification, just stop me anytime. Okay, so this is my background for those of you who know Charlie Bowman. I was in his lab at Purdue where I worked on Bayesian estimation for scientific imaging problems, which involved microscopy, tomography, super resolution, image inpainting for laser microscopy, and things of that nature. And one of the things that I'm going to be I'm going to be talking about um, this idea called plug and play priors. And for those of you who are not familiar with the idea, it's basically a flexible Bayesian estimation framework where you can separate the likelihood term that's based on the data from the prior term that's based on our belief on what the image or the quantity that we're estimating is. And I'm going to talk a little about the nuances in plug and play. Consensus equilibrium is our extension of this idea where we can completely get rid of optimization. So if you just have a set of equations, can you achieve consensus and equilibrium so that we get an estimated quantity with not necessarily through optimization though. Um, okay. So I'm a staff scientist at Oak Ridge National Lab in Tennessee. In East Tennessee, we're about 45 minutes west of the Smoky Mountains. And here I work on this cute little idea that's pesky in the national security sciences domain, where you have face recognition systems. In most cases, before a TSA officer or whoever is trying to look at videos or pictures of people who are coming in, um, before a face interaction happens, you look first at a digital format of them, a video or a picture, and there's human bias that's rampant. For example, the minute you see somebody, you have an opinion of them. I mean, just being human, we have this thing going on in our head. And oftentimes, with exposure, with education, with effort, we try to reduce it. But the first instinct of the brain is to have some opinion of a person. And sometimes it could be problematic. So we want to try to reduce that aspect. So what we're trying to do is try to make a mapping from a human face to something like a landscape image, where the mapping is bijective, and so it's unique, and it's not random. But at the same time, we are trying to decorrelate facial features from the landscape features. And that's important because every time you see an equivalent landscape image of a person's face, if a palm tree tells you that this person is brown or black or this person is a woman, what is the point of that? Because after a while, people are going to figure out, hey, I saw a palm tree, so we can make these inferences based on that, which kind of defeats the whole purpose of this. So keeping the mapping bijective and unique, but still trying to decorrelate the landscape features and the facial features is something that we're really excited about. And I'm also working on fraud detection systems in healthcare. Specifically, we are funded by the Centers for Medicare and Medicaid. What's happening is this doesn't happen a lot. This happens way less than 1% of the population. But when it happens, here's what's happening is certain physicians and healthcare providers are adding diagnoses. This happened with Kaiser too, and the only reason I can talk about it is this became public. But there are a lot of instances where it's not public, and I can't tell who's doing what. But some physicians are saying, okay, this person came in with what looks like pre-diabetes, or maybe morphing into diabetes, without many complications. But in the diagnosis, they actually write diabetes with severe complications, and that enables them to charge more money to Medicare and Medicaid. And this is fraudulent. And so this actually takes away money from people who really need those services performed for them. It's a challenging problem. The other thing we're also doing, which is not related to this, is ultrasound imaging to inform drilling, for example. Can we understand, based on some signatures we receive, acoustic signatures we get while we're drilling, and does it inform us which way and how much power to drill with? And so I just listed a few of the most frequent collaborators I have at the lab. And I do some mentoring activities. We are starting to design some courses to be taught within the lab. So if during an onboarding procedure, if somebody is, we hire smart people, but not everybody has the exact background in the projects that we hire them for. So can we create something like Coursera or Khan Academy, but inside ORNL to help? So I'm also on one of those, and I do some volunteering for IEEE in the Tennessee area. And this is mostly a repeat of what I said about Purdue, so I'm going to skip that. So prior to coming to ORNL, I was what's called a quant at Wells Fargo for about 4 years, and I worked on sparse representation problems and anomaly detection for financial crime modeling. And again, one of the bigger problems is in the finance industry, we have this idea of identifying what's called a key model risk. And for these detection problems, the key model risk is typically not false positives, it's false negatives. That's the problem. And generally how this happens is you have an algorithm and that flags certain transactions as saying, well, this is suspicious, so we've got to involve the FBI at some point, or maybe have human investigators look at these more closely. But the issue is the human investigators only look at the transactions that the algorithm flags as suspicious. The ones that we don't flag are not looked at. So understanding the impact and the extent of false negatives generated by the algorithm is very tricky. And in cases like I also worked on loan systems. So if somebody applies for a credit card and they get denied, there is a federal regulation that says you've got to tell the applicant why their application was denied. You can't because it's going to ding their score. It's going to cause them stress and at the minimum it's an annoyance. So we've got to tell them why. And FICO developed these systems called reason codes, I think, which is very basic. It tells you something which almost kind of doesn't make sense. So if I apply, so this happened to me when I was an undergrad. Back in the day, I applied to a bank, they denied it, and they didn't tell me why. Probably because I didn't have enough credit history. But it has to be an actionable item that tells you what can you do in the future to improve your odds of getting accepted. I'm gonna skip over the slide and maybe come back to it later, depending on if somebody has questions. But getting into the actual talk, there are two parts. One is computational imaging, and the other is can we build surrogate models for these deep learning models to explain a little better what's happening inside. So the basic idea behind plug and play priors is can we separate the data likelihood from the prior probability term? Why do we want to do that? We want to, okay, so there are a lot of things that enable you to do this. There are algorithms like ADMM, alternating direction method of multipliers. There used to be ISTA and then FISTA, and there was message passing. So there are so many ways you can accomplish goals like this. So we build our solution on ADMM, but in the coming slides, I'm going to tell you how we deviate from ADMM to make it more effective for what we want to do. Okay. So this slide it's too broad. I have this slide because in some of the talks I give, people are not very familiar with what I mean by a prior model. I don't expect this at Georgia Tech, but just for completeness of it. So if X is the quantity that we're estimating, in our case, it's the clean image. So let's say we're talking about a deblurring example where Y is the blurry image that we measure, and X is the clean non-blurry image that we don't have, but we want to get it. And by likelihood term, I mean it's a probability of Y given X. So what image or what value of X explains best the measurements that we have? So if we just maximize P of Y given X, we would have a maximum likelihood estimate. And oftentimes that's problematic. So I just want to give an intuition why it's problematic. It's because in some cases, like I worked on image inpainting or interpolation problems where you have so little data that just going on data, it's so underdetermined that you have so many images that fit the bill. Which one's your correct image is still underdetermined, which is why we are kind of compensating for that intuitively using a domain knowledge term, which we call a prior probability term, which does not depend on Y at all. It only depends on X or what we know X should be like. Okay, so in general map estimation frameworks, you have this framework where you're trying to maximize this term here. You're trying to maximize the right-hand side of this equation. P of Y is called the evidence, comes out of the equation because it has nothing to do with X. And in general, the way we represent this is L of X is a likelihood term, but there is a negative sign that sticks out, just so we can make it a minimization problem. It's not a big deal as long as we recognize L of X is the negative log likelihood, and P of X is the negative log prior probability term, just to make this a minimization problem. Now, So the idea, if you're not familiar with ADMM, here's where one of the ideas comes from, is both the likelihood and the prior probability terms are functions of the image, unknown image. And so you minimize them together. And even in the classical sense, where you don't have a great reason for why L and P should not be together in the same optimization loss function, one way of thinking about it is mathematically sometimes you don't want L and P, the summation of L and P to be very complex, okay? Because when you're trying to optimize that could lead to very many problems. I mean, it could be nasty looking. A lot of them are non-convex these days. So, I mean, people live with that anyway. But even apart from that, all non-convex functions are not equally easy to solve. So, in general, it may be helpful if you can have L of x and P of z, where z is a different variable. What you would do then is basically tear them apart into two different optimization problems. Now, but that's not true, because when you're solving for P of z, if z is a different variable than x, you're really solving a different problem, and that's not what you want to do. So in reality, what we do is, while we express this as a variable splitting operation, we have a constraint that x and z should be the same, value. This is not true in every iteration, by the way, but at the end of the optimization, if you want a feasible solution to this, x and z should be the same value. And I mean, people don't like working with constraint problems, so the unconstrained version of this would be something like an augmented Lagrangian, which is the last equation. It's essentially the same as the second one when you solve it right. Okay. Now, what ADMM does is, if you go back to the unconstrained optimization with the augmented Lagrangian, you basically, whatever you have within the argmin, you take partial, essentially you take partial derivatives, or however you want to solve your optimization problem. But you have the first part of your iteration, you solve for x and then for z, and then you realize, hey, you know what? X and z, we said, should be an equal value, but they're really not. So you have this parameter u that you can twiddle around to make x and z kind of come together. So that's the third equation you see here. And then so if everything goes well and you loop these iterates into convergence, and you get the map estimate. I just wanted to really quickly introduce the notion of proximal operators. Again, this is for a more general audience, but I'm just going to say this for completeness. If you have a minimization that looks like this, H is called the Moreau proximal operator, or proximal map of okay, that's a typo. I'm sorry, I apologize. It's a map of P. Okay, it's not a map of X. It's a map of the function P. Now, the interesting idea behind this is H looks like a map denoiser. So if you're denoising a noisy, if you're denoising a noisy function, but you also have a prior probability within the Bayesian setting to denoise it, which is given by P, this is exactly what the map denoiser would look like. So in general, a proximal operator could be thought about as a map denoiser. So okay, let's go back here, and this would tell us why this observation is important. If you look at both these equations, both of them look like they're proximal maps. They have the same form, which means, so the intuition behind these two optimizations, the top row, X optimization, is related to inverting the forward model. So if you have a deblurring problem, for example, the forward model is a blurring kernel, simplistically, right? So that's what's happening in the system. So the end result is your blurry image. So that minimization takes care of trying to invert that blurring kernel. And the second optimization relates to inserting our prior model into the equation. And we might have constraints about, one tiny example would be, our non-negativity constraint. So images are not negative. And so anyway, so the forward model inversion is usually straightforward in the sense that we know the matrix that corresponds to the forward model, and we have its own iterative process to minimize it. The prior model is interesting because we found certain operations which could serve implicitly as prior models, but we don't necessarily know the exact optimization formulation of them. I'll give you an example of that as we move forward. But the idea behind plug and play is you take this framework of ADMM and you have the second optimization, which relates to the prior model. Don't optimize it. Instead, replace it with a map denoising filter. Because from this, we know the filtering operation would correspond to minimizing the loss function that we've shown here. The interesting thing is sometimes if somebody told you, an oracle told you, that here's a denoising filter with a corresponding P of z, which is an implicitly defined prior probability model, but you don't know what that is. You just know it is good. Well, what I mean by that is, it's all the bells and whistles that come with it. It's closed, it's proper, it's convex, it has all the good properties, but you still don't know the explicit formulation of P. And so in real life, we ran into a lot of those denoisers where we can't really formulate the implicit prior model for it, but we know it does a fantastic job of denoising. We necessarily don't want the denoising operation, okay? That's not what I'm implying. What I'm implying is the operation that happens inside a denoiser while it tries to denoise your function. We are actually interested implicitly in that operation. I'll give you one example of that in the next few slides. But essentially, now we've established that we can use these denoisers, like it could be like a DNCNN, or like back in the day when I was a graduate student. Neural networks were not all over the place. We did other things like dictionary learning with KS3D or non-local means or BM3D. When you think about these, what these algorithms are doing in order to denoise an image, the things that they're doing and the things they're assuming about the image in order to denoise them are far more important to us than the actual outcome of the denoiser. So that's what we're trying to capture as a prior model. So we start with the general flow of plug and play is that we start with the data and then we do a forward model, an inversion for it. And then we can have some sort of a machine learning algorithm cast as a denoiser, and we can pull it implicitly as a prior model for Bayesian estimation. And then we do some ADMM update. By ADMM updates, I only mean you do some operations. When you do the variable splitting, you want the x and the z that I talked about to be close to each other. That's the update. And again, if you do converge, there's no guarantee for convergence as of this slide. And but anyway, if you do converge, you get a final image that is hopefully exactly the same as the map estimate that you would have gotten had you gone through the horrendously hard task of doing the map estimation like in the original sense of map estimation with one big optimization. One of the things when we tried publishing, we published this in multiple venues. One of the comments that we got was, "Is this plug and play or is it plug and pray?" So what the reviewer meant was, do you just plug a prior in and you pray that it converges? And so that was kind of like our incentive to come up with a more robust theory of convergence for plug and play. Essentially, it boils down to this. Mostly when you have a denoiser substitute your prior probability minimization, it works reasonably well. Doesn't theoretically converge. For most practical purposes, it converges well enough. But the theory that we established is if you have some mild conditions. So mild is a subjective word. No, I'm gonna be the first person to say that. But anyway, so people liked our convergence criteria, so I guess they're okay with the word mild on it. If you have mild conditions on your denoising operator, then the whole plug-and-play extension falls squarely back into ADMM. And now we can use the solid properties, convergence properties of ADMM, and to say plug and play converges. So that's a basic minimum idea. And we need a few ingredients. I'm not going to spend too much time on this, but just to give you an idea that it's not plug and pray. This is theoretically sound. I just want to spend a couple minutes on this. First, we want to show that H, okay, in case you forgot what H is okay, let's think about it as a denoising operator, okay? So H is a minimizer. So in other words, if you design a denoising operator to be a map denoiser, then H is a minimizer by construction, okay? So it's a proximal map. The problem is when you have, for example, we worked on material science problems. And okay, this is the time where I tell you why these denoisers might be important in plug and play. Now, if you've done material science or scientific imaging for material science, a lot of times you have these repeating structures that are non-local in your image, which means you might have, I'll show you some examples. So it's not local. So for example, if you try having a prior like, Markov random fields or some sort of a Gibbs distribution, you're relying on local dependence in your image. And in a lot of these materials images that we have, the dependence is non-local and it could be far-ranging. Non-local means is a denoiser basically that looks at patches in various pockets in your image and say, okay, this patch here is very far from the other patch, but they're very similar in how they look. So when you're denoising this patch, you're using the other patch to kind of inform how you denoise your original patch. So we were thinking this idea behind non-local means, while it denoises images, is exactly the idea that we need in order to characterize the materials images that we were applying our strategy to. So that's what I mean by using a denoiser as a prior. So, okay, in any case, especially for non-local means, some paper came out later on, but it's mostly still not clear what the P of Z or what the P function is. What is the implicit prior? You have an intuition behind it. The implicit prior is that you have similarities non-locally. But what is it mathematically? As a loss function, you don't have to know that. Anyway, so we want to prove denoisers like this could also be very, very close to a map denoiser. Or with minimal changes, they can be made a map denoiser. And then the other non-trivial part is, okay, you can assume that the map estimate exists. But we just want to also show that, okay, it's a map denoiser, but what is the guarantee that there is a map estimate in the first place? So you want to show that too. And then, well, if everything goes well, your whole plug-and-play setup falls back to ADMM. So this is just a sketch that the first thing we want to show is that H, in fact, is the denoiser is a minimizer. And there are a few conditions. So if you take the gradient of H, so just to give you an intuition, so for non-local means, this is like the weight matrix. So every pixel in the image exerts a weight on every other pixel. So if you have an image with n pixels in it, think of it as a long vector of n cross 1 vector. So you have n pixels in the image. So this weight matrix is essentially n times n. So it's a square matrix that's n by n. Now, whether it's only, so some people think it's only like lower triangular or upper triangle, the other part of the triangle doesn't matter because of symmetry. But in non-local means, sometimes the weight exerted by pixel I on J may not be the same as that exerted by J on I. So this entire matrix is useful. So think about this weight matrix as the gradient of the denoising operator. So it's nabla H. So we want that to be doubly stochastic. Okay, so which means essentially all the rows sum to 1, but also the columns sum to 1. And that gives you certain conditions like, that H represents a conservative field. So you have a zero curl condition. Intuitively, later on, after we did the math, it made sense why the zero curl condition has to come in. But anyway, and then you can think of, there exists phi, so that, H is like the subgradient of it. Anyway, so that's one part of it. So we want the weight matrix of the denoising operator to be doubly stochastic. And so if that's doubly stochastic, the eigenvalues lie between 0 and 1 included. And so H is non-expansive, and the phi you have is convex. Now you insert them. I know I'm going too fast, but you're welcome to read the paper or ask me questions at the end. So Moreau had I think he was a French mathematician who had a 1970s theorem, and if you combine these facts, he says, well, H is a proximal operator. And then the other part is now, how do you know the map estimate exists? Essentially, we want to show that, okay, if you define the product so the sum of the negative log likelihood and the negative prior probability, and call that a small h of x, and then you can define a sublevel set, which basically contains all the images intuitively, such that h of x is smaller than some alpha. Okay, so by the way, h of x is it outputs a scalar, so it's a single scalar value, which is smaller than some alpha. And the set of all these images which are true for this is called the sublevel set. Let's just call it a sub alpha. So in order to show that the map estimate exists, it's enough to show that this sublevel set is non-empty and it's compact. Again, I'm not going to go through the proof, but essentially the idea is that showing that it's non-empty is fairly straightforward. Showing it's because you're assuming things like P is proper, closed, and convex, and we only assume L is proper, closed, and convex, and P is convex. So based on that, so there are some prerequisites conditions for the proof, but we can show that the sublevel set is bounded and closed, and it's a real. So like I said, it's a scalar value, so it's a real number. So for real numbers, you can use the Heine-Borel theorem to say it's compact. So basically, you have non-empty and compact, so the map estimate exists. The papers that we published have, it gives you more insight into the proof, but I just made something of a hodgepodge of a proof for the presentation. So, but it's still accurate, but it's still not everything that I want to talk about. So anyway, so that's a theory part of plug and play in a nutshell. And I want to show you one application of why this might be attractive. So for example, if you're looking at a super resolution example, so we worked with the Air Force Research Lab in Dayton, Ohio, and we had these really powerful Titan microscopes, which are able to produce really high resolution pictures. But the thing is, in a lot of these scanning electron microscopy techniques, scanning is slow because you do something like raster scanning, so it's really slow. There was this bizarre statistic that, ever since scanning electron microscopy was invented decades ago, everything that's been scanned by it, every single thing that's been scanned by it by everybody in the world together is less than 1 cubic millimeter or something. I might be off about the number by a little bit, but that's approximately true, which tells you how slow this is in order to get a higher resolution image going on. So the scanning is slow. So even though the microscope is capable of producing a higher resolution picture, it's so excruciatingly slow that you want to just get a lower resolution picture and hope you can bring it to a higher resolution somehow computationally. Okay, so we're not necessarily going beyond the optical limit, but we are trying to get to the highest optical limits without scanning at that resolution. And so one of the applications we call is multi-resolution data fusion. What we try to do is scan just a very little, hopefully representative area of the image with high resolution, the highest resolution that you want to get. And then you scan the rest of the field of view in a lower resolution, and then you try to fuse them. And so we use plug and play to learn the features and the textures from the higher resolution patches. So you're essentially, intuitively, what you're doing is after you apply the inversion for the super resolution model. So super resolution essentially is, okay, you have a decimation operator and you have a blurring kernel, and maybe you're going to add some noise. That's how you go from a higher resolution to a lower resolution. So you model that, and you keep your fingers crossed that it's a fairly good model, and then you invert that. But in the prior and for the prior optimization, which is why I bored you to death with plug and play so far, is now you can apply something like non-local means. Because look at this image. So these the dots you see in the right side of the image where it says 8x super resolution output, those dots are gold atoms, and the carpet-looking thing to the lower left corner is a carbon nanosubstrate upon which the gold atoms live in this case. So you see a lot of repetition. So we want to capture that, which is why I also spoke about an algorithm like non-local means. We also did this with BM3D with very similar results. But essentially, what you're trying to do is apply one of those denoising operators during the plug-and-play step, where you insert a denoiser instead of the prior optimizer. And you're trying to denoise your low-resolution image over the big field of view with patches not from the same image. So non-local means typically you denoise from the patches of the same image, which are non-local. But in this case, we're actually denoising with patches from the higher resolution library of images that we acquired, spending a lot of time and money and effort. Okay, so that's the intuition behind how we are able to bring up the resolution over the big field of view at a fraction of the time and cost. So some examples. Okay, this is the same example, but some more results on this. The left column are different low resolution outputs. So if you look at the first row, it corresponds to one resolution. The second row is actually a lower resolution, and the third row is the lowest resolution. And the left column is not the ground truth. It's the measurement that we have. And the rightmost column in the red box is what we were able to accomplish using plug and play. Now, as comparison, we have like the cubic interpolation, and SISR just means single image super resolution, but I really forgot to insert the reference for this. This is from, I think, Michael Elot's team at Technion, I think. But anyway, so back in the day, we thought this was a fair comparison. Now we have better techniques, I think. But anyway, so if you look at the red box, we do produce better images. At the minimum for 8x and 16x super resolution, you see that, for 8x at the minimum, we produce something that's more or less usable. For 16x, it starts, becoming something like in a Van Gogh Starry Night or something, but maybe it's still useful. But in any case, you speed up the acquisition of these material images because you can acquire cheaper and faster images at lower resolutions, and then spend a little time on plug and play trying to bring it up. A same concept, different example. So this is the crack in the shell of a marine animal, and again, you see similar benefits in using plug and play. Now I'm going to blitz ahead a little. So we have some microscopy results where the black picture you see with all those grid lines, that's the measurement that we have over time. Oh, this was supposed to be, oh, sorry, it's a PDF. It was supposed to be a video. Basically, we acquire different frames where you're going through a Lissajous pattern of acquisition from your laser source. So every frame has different pixels which are acquired. And can we reconstruct this? So the right side you see, the top right picture is a reconstruction from the image that's right to the left of it. Again, this is using plug and play. Sorry, now it feels like a sales pitch talk, but I guess that's what it is. This is an example of electron tomography. So this is silicon dioxide. It's one tilt angle. It's not a full tilt series that I've shown, and you're seeing this from the top. And the reconstructions are from the side. Okay, so unfortunately, the two images are not looking exactly from the same perspective. And filter back projection is essentially, a linear operator that tries to invert the tomographic matrix that you have typically without a prior model. And with our different priors, like the Markov random field prior, which makes a local assumption, a local dependency assumption, that's the MRF prior, and NLM is a non-local means. The interesting thing is non-local means is not a map denoiser. So what happens to the theory that I spoke about so long? So we actually changed non-local means so very slightly to make the weight matrix doubly stochastic, and it went to being a perfect map denoiser. So we have theoretical convergence on the doubly stochastic gradient non-local means. So in all these cases, you see that the resolution is so much higher. You actually see those particulates from silicon dioxide. Okay, I'm going to skip this slide because I'm not going to get into consensus equilibrium. So part 2 is actually a smaller part where I'm going to talk about surrogate modeling. So the question is, you have this neural network that does whatever it does, okay? It could be image translation or it could be a classification problem. Now, can we have a tree ensemble, like a bagging method like random forest, or a simple decision tree even, or gradient boosting, which is a boosting technique? Can we have these ensembles explained as surrogates for the neural network? And can we understand anything about the decisioning rules that are happening inside? So, I mean, why it's important is we're spending a lot of money and getting a lot of money back from AI. I'm sorry, I don't understand the word AI, but that's a different tangent. But let's just say machine learning. So do we understand what goes on exactly in a machine learning model? What its limits are? Do we understand the uncertainty in it? Can we quantify it? So there are like many different challenges. Uncertainty quantification is something that is very big at ORNL, again, but that's not the topic of this talk. And then data curation is another big challenge that a lot of machine learning engineers work on. Explainability is something that is very close to my heart. So do we understand why a particular prediction is being made? And in case of adversarial attacks, this is really helpful because we know why the algorithm is not doing something right. Okay, and so this is basically a schematic of a CNN. So you have things like convolutions where you're trying to learn features at different scales, and so again, I apologize. This is too basic, so I'm skipping. So you have pooling. Okay, so now can you model convolution layers, pooling layers, but even before that, can you model a single neuron with a decision tree? So in this case, the sigma you see here, y equals sigma of something. So the sigma is the activation function, like leaky ReLU or whatever you want to use, and b is your offset. And the W's are your weights, and the X's are the inputs. So in this scheme, you can always model this whole neuron as this bunch where you have node splitting based on different criterion for each node, and then basically the tree on the right matches the output of the neuron here for the same inputs. And now once you have the model with the tree for one neuron, you can stack them up together and you can produce an entire row of these trees, which will replace one row of your neurons. And you can do the same for convolution. With convolution, you don't need an entire decision tree either. You can just use the smallest possible tree called a decision stump. And if this is your node splitting criterion, which is essentially you're asking if the convolution operator is bigger than 0 or not. And so you have two leaf nodes based on if it's a yes or a no. So it's fairly straightforward. There is nothing innovative about this slide. But the one thing that it does is it basically expresses the operation of convolution mathematically as a decision stump. So, okay, that's all it's doing. And you can do the same thing for pooling. Except that in pooling, what happens is you reduce your dimension. So there are a lot of these neurons which come out of the pooling layer which you don't use. So you think about it as either neurons not being generated and not being connected, or just you're ignoring their values. So either way, again, it's a very simple decision stump operation to implement a pooling operation. So now you have so you can model a neuron, you can model a string of neurons in a layer, you can model convolution and pooling, and now you just all string them together to produce these sequence of decision trees, which represents your neural network. So in principle, and we implemented this, so we know that it's doable, and it's not hard to understand. But okay, so how does this help? So once if you think about what a decision tree is, you're essentially asking a bunch of if-else questions. Okay, if, else, and then this. Okay, so when you're making decisions, if you say, back to my original example in finance, if you ask the question, why was my credit card application denied? And you say, well, if it's circular logic if you say credit score, because a credit score being low is not helpful because you've got to know why. You got to say things like, you opened that HSA account and you never made 2 payments on it, and it's been 145 days since you made payments. Had it been less than 60 days, then your score would be this much higher and you would have just about qualified for a credit card. Now, that's a helpful thing. So you have these decision trees that tell you if this happened or if this happened, then you're producing these outputs. So that's why we want to model these neural networks with decision trees or random forest, which is basically a whole bunch of decision trees in parallel. Now, but the interesting thing now is we can use the tools like the Shapley additive explanations to explain these surrogate decision trees. Essentially, think of this. So for those of you who are not familiar with Shapley values, it has its origins in game theory. The idea is, so you have let's say a soccer game, and one of the teams wins, okay, and so they get paid. And the losing team also typically gets paid a little, but far less. Now, how do you assign? One easy way of doing this is give everybody on the team the equal payout from the prize money. That would be one way of doing it. But then there are people like most valuable players. Somebody scored, 7 goals where others almost didn't do anything. So it would not be fair to the person who was most active in the game if you paid equally. So can you understand the contributions of each of those individual players and assign a payout for them? It's hard because they're all working in a team. And that's where you have these interactions between different variables. In this case, the variables are the players themselves. So that's the origin of Shapley analysis. But we can use the same thing. If you take different regions in an image and then ask the question, you know, why was the image classified to be a monkey, okay, as opposed to a dog? What portions, what areas of the image were responsible for such a decision to be taken by the model? That's the kind of questions that Shapley is going to help answer now that we have a surrogate model like a decision tree. And you can apply this for a variety of problems. You can, like image-to-image networks like tomography and microscopy networks, or object recognition networks. So this is like one quick example I wanted to show. So the source of the problem is from OpenAI. So they had a publication where, so you had a picture of a panda, which the algorithm, identified as a panda with 58% confidence. And then you add some noise to it. The noise is not as bad as I've shown because the epsilon is really, really small, the thing that you multiply with the noise. And so the right picture you see is the noisy picture, but to human eye, you can't even make out the difference between the left and the right pictures of the same panda. Now, but the algorithm has a 99% is 99% confident that it's a gibbon. Gibbon's a type of a monkey. Now, why did that happen? Because to humans it almost never happens. So I wanted to see if Shapley can shed any light on this, and it turns out that the small red square you see on the panda's face on the right, that's where 35% of the decision making was happening according to the surrogate model. Now I don't know if it's 35% because the surrogate model is not exactly the model we used. It's close enough. So, but for ballpark understanding, this is approximately true. And then you look at that portion just about the snout of the panda, and then you say, maybe it's confusing. I wouldn't be confused, but I can understand if the algorithm is confused. And maybe that's going to help us train better and for the algorithms to be more robust. Okay, so that's the majority of it. I had some slides about my teaching interests and blah, blah, blah. But I think I'd rather stop here and answer any questions than bore you more about this. Thank you very much.
Yeah, thank you, Suhas. This is Ghassan. Thank you so much. I think there's a lot to dig in, but hopefully we'll do that maybe some other time. But I have a question about, I think it was slide 12 or 13 when you talk about, plug and play, and you were talking about basically using another patch from another part of the image, kind of, to feed some knowledge into, the interaction between the two patches as you are really looping into the algorithm. From our experience, we had a couple of projects on material, like microscopic images of the materials. And the problem with those images, at least the ones we dealt with, that you will get some kind of artifacts. It's not all the parts of the image are treated equally when it comes to the the imaging side of it. So certain parts will have certain artifacts, and sometimes those patches will really kind of get you off track because of those artifacts, and they are really, at least in the ones that we had, the artifacts were much more common than we wished for. So I just want to see basically if you have experienced that, and if you have any thoughts about how that will play with your algorithm in here.
Sure. So maybe I have a couple thoughts on it. One is, the first thought is, well, if you're taking patches which have artifacts in them and using them as base patches for weighted averaging in non-local means, you might get your final reconstruction that has artifacts in the patch you're trying to denoise. It might very well happen. So you might just spread the artifacts more by using this. But then you can also control, there's a parameter in non-local means, so it has this exponential weighting. I didn't put it down. Essentially, when you're trying to decide what weight to assign between two pixels, what you do is you look at the neighborhoods of those two pixels and see how close they are. And the mathematical way of doing it is you take the L2 norm between the two patches and then you raise them in an exponential. you raise them in an exponential, and then you multiply that with, let's say, a beta that controls that's a knob you can turn. So what that means is how similar two patches are is something that you can control because it's a very subjective thing. This knob beta that I was talking about controls how similar two patches should be for you to give those two corresponding pixels a high weight for each other. And so if you think you have too many artifacts going on, the artifacts are going to show up as a difference when you take the L2 norm between the two patches. And then you can set a higher threshold for similarity between those two patches. So hopefully the artifacts are not going to be the patches with too many artifacts are not going to be considered for denoising your patch without any artifacts. So you can twiddle with the beta parameter a little bit. The extreme version of that is when you set beta to be too high. What happens is no patch, unless it's exactly identical to the patch you're denoising, would be considered a match. So you get back the input image as the output. So no denoising has happened. On the other extreme, you would get a very, very smooth image, very blurry image. So you can always set your beta parameter somewhere in between intelligently to try to prevent to have some denoising happen, but hopefully not spread your artifacts too much. But the third method, depends on what you want to do, is normally we to counter artifacts, we don't use the prior model for it. We try to account for it in the forward model. So in the matrix that you have that represents the forward model of whatever is happening in your problem, that's where we try to introduce some more terms that kind of counter that explain why these artifacts come up in the first place.
Right.
I don't know if it's helpful, but
yeah. Thank you. Yeah, I don't know if John is online, but if anybody else has a question.
I'd like to ask something, Suhas. This is Justin. So you had this very interesting slide where it's part of your explainable AI on like how you map a neural network to a decision tree. So I guess my question is like, so I guess one of the reasons that neural networks are popular are it's clear how to train them as you scale them. Is there also like a training framework for this type of decision tree, or does you just take a neural net that you have and have it undergo this mapping? Like, does this give us a new way to learn is my question, or just to execute what we've already learned?
So far what I have shown on the slide is the latter. If you've learned something already, it basically distills it down to a network of trees.
Okay, good. And to deploy this, I still learn using the neural network, train using the neural network, and then I can employ it with the tree so it's interpretable. Is that the idea?
That is the idea, but then this is serving. So far, we are not training decision trees to replace neural networks. We are only using decision trees as diagnostic tools so we understand what's happening. But one of the feedback that's coming out of this is sometimes we understand this is where, so the given example I showed at the very end, that corresponds to some areas that the information flow for that patch goes to some areas of the neural network. So we are trying to change the parameters in those areas of the neural network and trying to see if the error reduces because of that. So it informs your learning and it informs the architecture choices you have for the network, but we are not training the decision tree or the random forest itself to replace it.
Okay, I understand. Good.
Okay, any other question from the audience? Going once, going twice. Yeah, I mean, I know it's really a pity it's virtual, but I want to thank you, Suhas. Thank you so much. Suhas, if you don't mind, do you have a couple of minutes just kind of chat